Yeah.
On one trade my entire 10 is literally, I just realized this 10 was playing with the equity. Wow. I have won once. There's usually 12 people, so I feel pretty accomplished. The one guy's won 3 times, though, so he's actually going to pay for the dog. And then we have this family that's like living in the farms, except for the fact that
Okay, well, welcome to the continuation of the class with meeting number 6. Right? It will be, I think, very easy for you today. A little bit harder for me because the subject that I'm going to deliver is typically swallowed in 5 minutes in most of the classes, and I will expand it to like 40. There are a couple of things that are considered self-evident, and they are skipped in lectures and classes. And then everyone assumes that the things are self-evident. I'm not sure if it is self-evident. It wasn't for me at the time undergraduate. It is one of the reasons why you are taking notes, because some things may be evident for me, and I will just present them very quickly, and for you to do some questions, and some things I may mumble for half an hour, and for you it will be very clear for a couple of words. And if you take notes, you establish your pace because you're transforming what you hear in your own stuff. So on the coming Friday, there will be presentations on these subjects. Well, you can find a little bit more on this postulate in 1 to 6 on open sources, and there will be action, democracy, sign up sheet. So most of the subjects are dual presentations by 2 authors, some are by single author. So if it is dual presentation, just contact your partner and make one set of slides for 2 and just present by 2. Agree when which words are told by one person, which words are told by another person. Okay. Answers the question. So if you do not found open sources, this is kind of summary of what is expected. The whole meeting will be for 15 minutes, so tonight number of presentations by 50, so we will go over like 8 minutes total for one presentation. So it is your choices, right? Since I'm already recording the name, so you can see it. And it looks like first 4 are dual, and most complicated last 2 are single.
Does anyone want a partner?
Contact each other. And I am expecting slides by about midnight on Thursday, so that I can upload them here and we do not spend time on coming and see that something doesn't work. You can be aware that recently all devices are updated to a new format of USB 3. If you're recording something on memory stick with USB 3, there will be no place to stick it in here. Better to put out on computers. Yes. We have in our syllabus, we have a lab on Wednesday night from 5 to whatever it takes, like hour or 2. It is kind of office hour, problem solving, and most of the computational things. I will be here today, and you can just come and make yourself acquainted with the space. But I may show something, but it will be basically to get acquainted with space and check if computers have great software installed. So if you have something really good for your life or for other courses, you're welcome to stop by. So I think it is the same building, first floor. To So we are in the class of physical chemistry. Physical chemistry is reduced to quantum theory because ions are classical, point charges and electrons are moving with high speed and they are distributed clouds in space, they are waves. And to describe waves, the regular math, regular intuitive thinking doesn't help, so we need to describe waves. We need specific equations which will explain properties of electrons in and atoms and molecules, and then we'll be able to predict, or at least to pave a way for predicting chemical stability of specific molecule properties like, say, color. The general idea that we were dealing with philosophy rather than with science for a long time, but if you do have propagating spectrum, then as long as it propagates in space and time, it accumulates phase. And there is such abstract concept as wave function. As phase is accumulated, this wave function does oscillations in complex space, right? And after speaking a long time about this concept, we are trying to use it as not very solid, but some fundamental, some cornerstone, and we are trying to come to more rigorous equations, which will be solving for specific problems at later time. So one of the most important equations that we derived last time based on this concepts of propagating waves. We also were talking about the goal of the course to predict future for three ways. The time-to-time Schrödinger equation. By now, it is most important. And the time-to-time Schrödinger equation, which so time derivative of wave function is proportional to wave function multiplied by the operator. And last time we were speaking about what is operators. So, what are operators? You do not need to answer to yourself. So, operator is something that is placed in front of wave function. So, it is an abstract concept that changes the wave function. Maybe not changes, but it's something that operates, affects. And here we do have, well, in the previous slide we had Hamiltonian operator of energy. We also got printouts with table how to convert classical variables into quantum operators. So this is one of the most counterintuitive steps that we should go slowly but surely, so that later will be easier. So some of the operators, especially the operator of momentum, is represented as derivative over opposition, which is very strange. Momentum is like velocity, but how does it relate to position? So try to think about it in yourself, and I will spend most of the time of today's meeting into getting this idea more clear and familiar. Another thing that I'm going to present is how to reduce so-called time-dependent Schrödinger equation into so-called time-independent. There will be two things: time-independent Schrödinger equation and more details of on the nature of operators. So right now, it will be very normal to have irritation against operators. They should become our, maybe if not close friends, at least reliable partners. What else did we have last time? What is on the last line? So if we are converting our focus from classical world and intuitive variables for physical quantities and energy to quantum operators, we are losing the freedom to swap the order of variables. So one needs to pay penalty for swapping the order. And this penalty we pay after swapping order of some operators is called commutation. So here is an example of two simple swap. It will be 1, 0. And here we write it as an operator, but in our head we should assume always that after operator there is an unknown function. Then there will be not a big conflict for cycles and so on. I will go over this once again many times. Right? Why do we need operators? What are the operators? Well, first thing, they are integral part of the Schrödinger equation, which is needed to predict future. You cannot propagate wave function, you cannot predict future of electrons without knowing the operators to construct energy operators. Operators are needed just to construct the energy. Second thing is the, to some sense, main practical goal of the course. To predict outcome of an experiment. So if you are exposed to research or just some lab works, there is a synthesis part. Synthesis and characterization. If you're doing this characterization, typically you put your sample into some web box, push the button, and then you have some graph on the screen. Okay? So graph on the screen can be like absorbance or mass spec or whatever. But I wouldn't brag that quantum theory is so powerful and you want immediately for everything. But in many cases, it helps by following the following idea. So if you know what you are measuring, what is observable of your characterization, for example, like intensity of how it emits light, or something else, there is a way to construct classical variable and then quantum operator for this observable, for the stuff that you are measuring in your instrument. And then if you do know your wave function at a given time, you convolute together the function, an operator of your observable, and then an operator of this variable, and then you get expectation value that you are measuring, that your instrument will give you. So there are limitations to any nice theories, to any nice arrangements, but in ideal, any experiment, any characterization experiment you can do in the characterization lab can be predicted based on with the following reason. So it is the second reason why we need operators. First reason to have operators is to stuff them into Hamiltonian, and second reason is to predict outcomes of experiment. Make sense? And you have seen this thing. So I will focus only on this momentum. Operators I typically have hat on the top. And that momentum operator is represented by derivative on space. There is no reason to go further until we get comfortable with this notation. So it's counterintuitive. When I was in my undergrad, it was assumed that like maybe I just put up the right lecture. But it was always referred to this relation as something like basic that everyone is assumed to understand. And now I'm trying to reproduce the logic behind it. So there is a logic. It is not arbitrary statement for memorization. Well, the first one because it's related to this course. But we never practiced to solve any real problem. And before we try, we will start slowly but surely with some really simple things. But before we go to a solution of real problems, we need to set up a protocol, an algorithm to solve. We have equations, but they are crazy, complicated equations. If you were taking differential equations, you may have a general idea how to solve it. But it's better if we agree on these protocols and discuss it before the actual problems. So we can assume that wave function is a product of time part and space part, right? Time part depends on space part depends on x. And then if we write down so we can copy this general formats. So if you plug in here the product of time part and space part, then we can practice this product rule. For space part times or time part times x plus time part times dt of x equals well, the function x, okay, but it doesn't depend on time, so this will be 0. And we are going to assume some specific functional form for time and space part, which is not rigorously allowed mathematically, but later on we will see that this assumption will work out almost every time. So those of you who were taking differential equations, if they are linear, if all derivatives are added together, if there are no powers of the derivatives, what is the typical way to assume for general solution of differential? Especially if it is yeah, it's trivial solution. What is a non-trivial solution? Like if you have say d y dt equals 1. If you were taking differential equations, it should
Or net e to the x or whatever.
exponential, yeah? Right?
Yeah.
So exponential is very universal form. It appears everywhere. And if you go in your differential equations class, if you go to more complicated equations, sometimes your solution is just exponential multiplied by polynomial, or exponential with some complicated power. But exponential is a universal thing. So Why would we assume? Again, what I'm telling is not rigorous math, it is just hypothetical assumptions. What if we assume that our time part is just e to the power some constants times t? And the idea for such assumption is that here we have first derivative over time, and we know that solution of first order linear equations will be exponential. So what will be the consequences if we assume this function of value?
What's that say?
Huh?
What's that say that you just wrote?
I wrote functional form.
Oh.
I apologize for substandard calligraphy. So everywhere we have t capital, we will replace it to e to the power ct, constant and variable t. So if you have here time derivative over e to the power ct, what will be the outcome?
C times e to the ct.
Yes. So here c is e to the power e ct. Good? You're following. No objection. Here we have c to the power ect. Here we have e to the power c ct. And this term is 0. So both left and right part have the same function, e to the power ct. So nothing bad if we.
So then, how did you get that one part equaling 0?
If x capital doesn't depend on t, then in respect to, so x is a function of x, and we are taking variable over t. So in respect to variable t, it is a constant, and derivative of a constant is 0. So now we do have this e to the power ct on the left and right that we can cancel on both sides, right? Okay. And if you cancel them on both sides, then what will be the rest? I'm bad with space management. I probably put all of it here. So it will be left over c times x on the left and minus x on the right. So through this trick, through the assuming specific function form, we got rid of the derivative over time. And we got rid of the dependence of time. So right now we have only an equation which also includes some derivatives, but it will be only derivatives in respect to position. So even if our space was one-dimensional, position, x, and time, mathematically it was two-dimensional problem. Now we got rid of the time dimension. Now it is one-dimensional problem. So we can declare right now, this is equation for space part of wave function. It doesn't have dependence on time. If it doesn't have dependence on time, it is time-independent Schrodinger equation. Yes?
So in the green circled equation, would the x on the right technically be x0?
So it is, I can't write in the screen yet. It is x capital of x. Okay?
Okay, I just
So then you can't cancel those out.
No, I cannot cancel. Right here, I was able to cancel because there were no operators acting in this function. And here, there is a operator. And when operator acts on function, it can do crazy things. There is no guarantee that it will be the same function and then it can be cancelled. I was too impatient, and we can redefine the constant. So if we divide left and right part on this factor minus I over h bar, here. And then you can pull this combination of constant times h divided by minus I. By dimensions later, we can see that it will be energy. And it will be standard canonical form for time independent Schrödinger equation. Okay, I'm done with the first part. Here I'm just previous here, but you will see nothing new. The same thing. So we go from time dependent to time independent. In some sense, the equations that we get, so operator x is x, and typically it is used method 5 because x and x is too ambiguous. H capital divided by 5 x, it is time independent Schrödinger equation. So typically Hamiltonian is differential operator. E is just a number. And the nature of this equation is that typically it has more than one solution. Like when we all were in the prime school, we were solving questions like 3 times x equals 2. Find x. There was one solution, one equation, one solution. And here, for this sort of equations, there will be one equation generates many solutions. So it is so-called eigenvalue problem. Oh, lift hands if you ever heard this. Oh, really?
I don't remember.
Okay.
I heard it.
Okay, but more than half.
Yeah.
So, who speaks German? Who doesn't speak German? Okay. Last time I was distributing some printouts for your Fire Kingdom. Did you ever look on it? So, did you look on the preface by Schrödinger? The one-page stuff. Does he explain this work? It's his invention. Probably he. So this eigen is in German, but in English it will be proper or own. So it is kind of ambiguous translation. So eigenvalue problem or proper value problem or own value problem. Why own? Because for each operator, for each equation, there will be a set of discrete set of so many large, but not any value of this parameter will satisfy the equation. So only selected values of this parameter will allow this equation to be solved. So the value of the energy parameter that makes it soluble is a property of the equation, or it is belongs to this equation. Its own. If I am the equation, it's my own value, or German eigenvalue. So this is each eigenvalue for each value of this parameter, the functional form of the equation will be given. So if we set up a Hamiltonian and try to solve, there will be a set of values of E1 in functions, 5, 1, 2, 5, and it will be more than 2. So standard classes in physical chemistry, quantum theory focuses primarily on solving this equation, finding this particular. Your images from this S, P, D, they are these functions for hydrogen atom. Okay? So you see the connection. Functions are known, energy unknown, Hamiltonian is known. All solutions, all eigenfunctions. Yes. Quantum theory is a set of tricks to solve Schrödinger equation in very narrow sense. So we know, it doesn't know function, we don't know energy, but we need to know the theory in order to solve the equation. So we need to cast to formulate energy of a system in form of operator. Energy is like summation of kinetic and potential. Kinetic energy is always standard, potential is dependent on where. If you have ion, it is attracting. So it is potential is more and more negative in the receiving of ion in very quick sense. But we want to be more general and focus on this more details. So what is the skill? What is the art of formulating operators? Okay. I did this one because I didn't like the slides. So, and we have about 15 minutes. So we are going to get familiar with an idea of why momentum operator is cast as derivative over space. Why do we focus on momentum operator? Because kinetic energy is momentum squared divided by mass. So momentum, we cannot do quantum theory without momentum. Another thing, for those of you who didn't take differential equations, we need to get familiar with eigenvalue problems and get encouraged that such problems can be solved. Sometimes they are really simple. Not always. Most frequently they're not simple, but there are several examples where they simple. So it's I wouldn't say last, but it's one of the last times when we refer back to philosophy. Later on, we will use less and less philosophy, hand-waving ideas, and more rigorous. So, through our discussions of waving nature of accumulation of phase along the motion that makes the function to accumulate, how can we project these ideas onto distribution of wave function in space? Maybe starting from Bohr's model, when you saw that as we go along the trajectory, something oscillates and we accumulate more and more phase. So the phase accumulates along the trajectory according to the momentum times x, right? If you divide it by Planck constant, it should be integral. on one hand. On another hand, we do have function divided by h bar, and both of them are raised into power of exponential to be approximately corresponding to wave functions as function of position. Do not take my words literally. Do not reproduce it in public. So this is not general solution for any wave function in space. We will have much more different solutions. But if you look on any wave function in the narrow vicinity, when it looks like free propagating electron, the solution will be very similar to this. If you know the momentum, you know the range, but it's not a literal solution. It is only a starting point for logic. So suppose we do this. What's the name of your best friend in this course? Mathematics.
Operator.
Family name. You are right if you speak in public, but if you look for mathematical trick rather than equations, look back for like 300 years ago, how to analyze the oscillating exponentials. Yes. So we do have a sine of p x divided by h bar plus I sine p x divided by h bar. Now there is a great challenge for me as a not very successful artist. I'm going to draw this function. And if I fail, I have a backup on the next. So if you have real and imaginary parts, we do need to have two axes. So this one will be real. And this will be x. So at position 0, value of a sine is 1. After a full cycle, it will be minus 5. So here's one. This, right? So it is projection onto this real part. Now changing the color and making imaginary part. Which also need to change from minus 1. So sine at position equals 0 will be 0. Right? Then it will start growing. Down, right? So the red and blue lines are projections, but we want for both red and blue line, we want two-dimensional vector. So at time at position 0, the vector will go here. At quarter of the period, it will be up. At half of the period, it will go from us. At 3/4 of the period, it will go down. At full period, it will go forward. And then it repeats the pattern. Up, backwards, down, forwards. Right? So the tips of the vectors, it is like trajectory, how this complex wave is changing. And now I'm connecting these tips by a continuous line. Oh, I need to be clear. it should look like a spiral, right? Like a spring. So it makes rotations and translation at the same time. Good. So now you are certified experts in three-dimensional drawing of complex functions. So between the maxima, the distance between the maxima is what? What do you call it? Wavelengths, right? Spatial period. So in some sense, we can tell that we equate this sign of px over h bar to the sine of 2 pi over lambda times x. Right? Objections, you're following. So instead of px over h bar, you can write 2 pi over lambda times x, because it is a wave with slopes, and we can identify the wavelength. So if the real part of this wave is represented by both of these functions in the same measure, it means their arguments are equivalent, right? Good. So we can write that 2 pi over lambda equals p over h bar. Please raise hands if you object. This is the thing that I was missing when I was taking the grades. If you're getting there, you have solved the problem.
So where did the 2 pi over lambda come from again?
If you design an equation for oscillating for cosine of a given wave spatial period, when the x equals lambda, then it will be 2 pi. So it will come to 0. After a full period, it should come to the same phase as it was before, as it was in the initial position.
Okay.
Okay? So 2 pi over lambda equals p over h bar. And we can recast it as remove h bar here and put it right there. So in the intermediate wave, it is not yet fully quantum case, momentum is inversely proportional to wavelengths of your wave, right? We already shown based on this ideas of oscillating waves. It is not the whole story. We're going to add something there. But it already gives us the idea that momentum is inversely proportional to something related to distance. Now, suppose again we do have x over h bar function of y. Now, let's do so. It is the same story. We are looking from different angles. Let's make a mathematical experiment and apply derivative over position. So, what will be the result of application of derivative over position to this exponential? So the exponential function will reproduce itself, and everything except x will float. Let's start with this plus. Float to the front. P or h bar. Any objections at this point? I'm not going through straightly. I'm catching you and agreeing on some. Please.
Is that on the right hand side of the equation? Is that positive? I or is that
It's
negative?
positive.
Okay.
Why
is it positive?
Because we started from positive here.
Okay.
Depending on my mood, I put positive or negative. Different years.
Okay.
Okay, so you do not argue with this thing. Very good. Now, let's divide that and break part on this factor. H I x e I x equals p e x. So right now we were assuming that our particle has a certain momentum, that it is classical variable. So this p. But by applying this operator to the wave function, we extract the value of momentum out of wave function. And here is the most strong assumption. If we write here any arbitrary function x, if we apply this h bar over I ddx to this wave function, we will get the wave function itself times value of momentum for the wave hidden in this wave function. Okay?
So where was that just saying if we do this, this will happen?
If you apply this derivative over space with a certain factor, the wave function will be it is equivalent as wave function is multiplied by the value of momentum corresponding to the, by the way, dense fringes, high momentum, sparse fringes, low momentum. So basically it's a way to learn how dense are fringes in these oscillations. Okay? And due to this, if you accept this equation, then you would accept that this combination of derivative and factors will be a quantum operator of momentum. Okay? I'm not expecting to have more slides. So if you can put it into box and memorize, it's maybe the only equation you need to memorize in the course. The rest can be derived from it. Check. Yes? By the way, okay. This was an example of, this is an example of solving eigenvalue problem. Not for Hamiltonian operator, but for momentum operator. So unknown function, unknown operator, actual function gives proper value. So this P is eigenvalue, this is operator. So if the function was this so-called plane wave, if you apply a momentum operator, we get value of momentum. And this is certainly last slide. From time-dependent Schrödinger equation, we go to time-independent. That has several solutions, several proper values of energy, and several functions, wave functions. Energy and wave function, energy and wave function. And if they're good wave functions, they're orthogonal, and based on wave functions, one can predict outcome of experiment. Enough. Thank you for the questions. Looking forward to your slides by Thursday midnight. And if you have free time, be my guest in the lab downstairs today.
You said our lectures that we're giving have to be 8 minutes long?
No longer than 8 minutes.
Okay, so if we give a lecture that's 4 minutes long, it's okay?
Oh, sure. I will fill the space with questions.
Okay.
Does anyone still need a partner?
Keep it
Are you
there.
able to pull that list of partner stuff again?
Yes, yes, please.
I'll hit the first one. Yeah.
I have a couple slots. Yeah, that's fine. Your email. Yeah. Are you on the? Maybe send out.
Yeah.
You and just Dylan.
Yeah.
Okay.
So,
We can.
number 5 and number 6 go.
Ben or Joey here?
Yeah.
Joey? Yeah.
Ben.
Ben? If we can, if you want. I can do it.
It might be a bit complicated.
That's good. Yeah, that's fine. I looked at it.
Yeah.
When you're ready. Yeah. 7:09.